Optical transmission networks are designed as carrier-grade infrastructure with extremely strict requirements for service continuity and reliability. Protection switching refers to the process of automatically transferring traffic from a failed working path to a pre-configured backup path when a fault occurs. According to international standards such as ITU-TG.841 and domestic standards like YD/T2713-2024, all standard protection schemes for optical transmission networks, including linear multiplex section protection, ring network protection, and optical channel layer protection, require a protection switching time of less than 50 milliseconds for networks up to 1,200 kilometers in length. Some advanced solutions even support 5-millisecond fast switching for high-priority financial and low-latency services. This 50-millisecond threshold is derived from the human ear's perception limit for voice interruptions. Interruptions exceeding this duration will cause noticeable call drops or audio distortion, which cannot meet carrier-grade quality of service requirements. Real-time services such as video conferencing and online transactions also have similarly strict requirements for interruption time. Second-level protection switching would result in complete service interruption for all real-time applications, severely impacting user experience and business continuity, which contradicts the fundamental design objectives of optical transmission networks as core communication infrastructure. To achieve millisecond-level switching, optical transmission networks use technologies such as pre-computed backup paths, hardware-level fast switching, and dedicated overhead bytes, such as K1/K2 bytes in SDH, to transmit switching signaling. Therefore, this question chooses B. Subnetwork Connection Protection, SNCP, is a highly flexible end-to-end path protection mechanism defined in ITU-TG.841 for synchronous digital hierarchy, SDH networks. Contrary to the claim that it only supports single ring protection, SNCP is explicitly designed to provide reliable protection for services traversing multiple interconnected subnets, including various inter-ring topologies. It supports all common inter-ring networking configurations such as ring with chain, tangent rings, intersecting rings, and dual-node interconnection, DNI, between two or more rings. As a service-level protection scheme operating at the subnetwork layer, SNCP uses a simple 1+1 dual feeding and selective receiving mechanism that requires no intersite protection protocols. At the source node, traffic is simultaneously transmitted over both the working and protection paths, which can traverse completely different rings or subnets. At the sink node, the receiver continuously monitors both paths and automatically selects the one with better signal quality. This topology-independent design allows SNCP to seamlessly extend protection across multiple rings through intermediate bridge nodes without complex coordination between different ring protection domains. Unlike multiplex section protection, MSP, which is primarily limited to single-ring operation and requires complex inter-ring APS protocols for cross-ring protection, SNCP achieves inter-ring protection purely through end-to-end path configuration, making it the preferred protection mechanism for large-scale multi-ring SDH networks. Therefore, this question chooses A. The synchronous digital hierarchy, SDH, is defined by ITU-T recommendations, with the STM1 signal serving as the fundamental building block at 155.520 megabits per second. Higher order signals are formed by byte interleaving multiple STM1 frames, with each subsequent rate being a precise multiple of the base rate. The standard STM16 rate is 16 times that of STM1, which equals 2,488.32 megabits per second. The stated value of 2,500.32 megabits per second is therefore incorrect. The discrepancy stems from a common misconception where the rate is incorrectly calculated as 16 multiplied by 156.25, which yields 2,500 rather than using the exact STM1 rate. This highlights the importance of using the official ITU-T-defined rate of 155.520 megabits per second as the multiplier for all higher-order SDH signals. Therefore, this question chooses B. Wavelength division multiplexing (WDM) is a core optical transmission technology designed to maximize the capacity of a single optical fiber. Its fundamental principle relies on combining multiple optical signals that use different wavelengths or optical frequencies into the same fiber for simultaneous transmission. Each signal is assigned a distinct wavelength, allowing them to coexist without interfering with one another. The statement in the question incorrectly claims that signals of the same wavelength are multiplexed, which contradicts the very definition of WDM. Signals on the same wavelength would interfere destructively, making them indistinguishable at the receiver end. WDM's strength lies in its ability to treat different wavelengths as independent channels, vastly increasing the fiber's total bandwidth without requiring additional physical cables. Therefore, this question chooses false. An erbium-doped fiber amplifier, EDFA, is an optical amplifier whose gain characteristics are fundamentally determined by the energy levels of erbium ions in the fiber core. Its gain spectrum is fixed, primarily covering the C-band, 1,531,565 nanometers, and L-band, 1,565-1,625 nanometers, centered around the 1,550 nanometer window. It cannot operate in the 1,310 nanometer window, which is a separate optical transmission band, because the erbium ions do not provide stimulated emission gain at those wavelengths. The claim that its gain range is not fixed and that it can amplify both 1,310 nanometers and 1,550 nanometers signals simultaneously is therefore incorrect. The 1,310 nanometer band requires different amplifiers, such as praseodymium-doped fiber amplifiers, PDFA, which are not as common in commercial networks. Therefore, this question chooses false. To access the complete question bank, please click on WhatsApp below the video to contact me.